Hello everyone, this is BB Sangmay and today I am going to discuss about the theories of failure. In the previous video we have seen how to identify the principal planes and principal stresses. Also we have discussed about the various principal stresses. So do subscribe for the upcoming videos of machine design. So before going to see the theories of failure, first we need to understand what is failure. Failure of a member is defined as one of the two conditions: fracture of the material of which the member is made. This type of failure is characteristic of a brittle materials. Second is the initiation of inelastic, that is plastic behavior in the material. This type of failure is one generally exhibited by the ductile materials. Okay, so here in this figure you can see that how the ductile materials actually fails. Here you can see that the failure of ductile material takes place by formation of neck, and here you can see that how the brittle materials fails. Now the question is why we need to study the theories of failure. As we know that to check the strength of any ductile or brittle material, we usually go for the tensile testing. Okay, and the yield strength is the criteria for the design of ductile material, and ultimate strength is the criteria for the design of brittle materials. And from the tensile testing we usually get the yield strength in tension or ultimate strength in tension for the particular material. But if you see that the tensile testing is the uniaxial testing, where the component is subjected to only one type of load, or the load which acts in only one axis. But in actual practice, if you'll see, many practical applications are there. If you'll take the example of gear mounted on the shaft, which will be used for the transmission of torque. So in that case, that particular shaft can be subjected to torsional stress, and along with that there will be a bending stress because of the radial force applied by the driving gear on the driven gear. Okay, so there is a possibility of a failure of shaft in bending and torsion also. Okay, so here in this example the shaft is subjected to a combined type of load. Okay, so the only design of shaft on the basis of tensile strength is not suitable. So because of the combined loading, the earlier failure of shaft can take place. When an engineer is faced with the problem of design using a specific material, it becomes important to place an upper limit on the state of stress that defines the material's failure. If the material is ductile, failure will take place by yielding, or if the material is brittle, then the failure will be take place by a fracture. So these modes of failure are readily defined if the member is subjected to a uniaxial state of stress, as the case of simple tension. However, if the material is subjected or the member is subjected to biaxial or triaxial stress, the criteria for failure becomes more difficult to establish. Already we have seen the example of biaxial or triaxial state of stress in the previous video. In this particular section we are going to discuss 4 different theories that are often used in engineering practice to predict the failure of material subjected to multi-axial state of stress. A failure theory is a criteria that is used in an effort to predict the failure of a given material when subjected to complex stress condition. There are several theories available, however only 4 important theories are discussed here. First is the maximum principal stress theory, that is Rankin's theory. Second is the maximum shear stress theory, that is Coulomb, Tressa and Guest theory. Third is the distortion energy theory, which is also called as the Huber, von Mises and Henke's theory. Fourth is the maximum strain theory, which is called as the Saint-Venant's theory. Fifth is the maximum total strain energy theory, which is also called as a Hayes theory. So let us discuss about first the maximum principal stress theory. According to this theory, it is assumed that when a member is subjected to any state of stress, it fails in the manner of fracture for the case of brittle material and in the manner of yielding for the case of ductile material when the principal stress of the largest magnitude, that is sigma 1, in the member reaches to a limiting value that is equal to ultimate normal stress. The material can sustain when subjected to simple tension or compression. The statement of this theory is the failure of the material or the failure of the component which is subjected to biaxial or triaxial state of stress will take place when the maximum principal stress, that is sigma 1, induced in that component will be equal to yield strength or the ultimate strength of the material which is used for the tensile testing. Okay, so first of all let us take a component. So here I have considered a component on which I am going to apply a stress in x direction, which is sigma x. Similarly, it is the normal stress. Here you can see that it is acting perpendicular to the area. Next is the stress, which sigma y, normal stress, which is acting along the y direction, and the same component is subjected to shear stress, that is tau xy and tau yx. So here you can see that already we have discussed in the previous video. The first letter x represents the area over which the shear stress act, and second letter represents so here you can see that the first letter represents the direction of stress and second letter represents. So here you can see that the first letter represents the area over which the stress acts and second letter represents the direction of stress. This is the tau xy acting over x area towards y direction. This is the tau xy acting over x area and the direction is towards the y direction. Okay, so similar tau yx. So here you can see that the component is subjected to triaxial state of stress. So in the previous video we have derived few equations of a maximum principal stress, minimum principal stress and maximum shear stress. So first is the equation of maximum principal stress, sigma 1 is equals to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 bracket square plus tau square xy. This is the equation of maximum principal stress. Second is the equation of minimum principal stress, that is sigma 2, sigma x plus y by 2 minus root of sigma x minus sigma y by 2 bracket square plus tau square xy. And third is the equation of maximum shear stress. Okay, so here actually we are discussing about the maximum principal stress theory, and according to the statement what it says that the failure of a component which is subjected to biaxial or triaxial state of stress will take place when the maximum principal stress, that is sigma 1, induced in the component becomes equal to yield strength of the material or the ultimate strength of the material or the component under tension. Okay, so here we can see that when sigma 1 will be equals to SYT, okay, there will be a failure. So while designing the component according to the maximum principal stress theory, we should take care that the sigma 1 should be less than SYT or SUT of the particular material. Now what the statement of maximum principal stress theory says, it says that the failure of a mechanical component subjected to biaxial or triaxial state of stress take place when the maximum principal stress, that is sigma 1, induced in that component becomes equal to yield strength of the material of the component or the yield strength of the component under tension. Okay, so here you can see that to plot the safe area or safe region under which the component will be safe, Here you can see that the sigma 1, the upper limit or the maximum limit of sigma 1, it should be less than or equals to SYT or SYC. Here SYT is positive, it is the yield strength in tension, and SYC is negative, it is the yield strength in compression. So here I am assuming that the yield strength in tension is equal to yield strength in compression. So let us plot the region of safety. So for that I am going to draw a horizontal axis on which I am going to plot the maximum principal stress, that is sigma 1. Similarly I am going to draw a vertical axis on which I am going to draw the minimum principal stress, that is sigma 2. So this is the origin. On the origin, on the left side of origin, I am going to consider maximum principal stress as negative. On the right side of this origin, I am going to consider the maximum principal stress as positive. Once again I am going to tell you that the negative symbol is for the compressive stress and the positive symbol is for the tensile stress. Okay, similarly on the upper side of the origin I am going to consider as a minimum principal stress as a positive, and at the lower side of origin I am going to consider as minimum principal stress as a negative, that is the compressive stress. Okay, so on this here first this is the condition where the component in the first quadrant, the component is subjected to the maximum stress is also tensile type and minimum principal stress is also a tensile nature. So this is the type of same nature of stresses. In the second quadrant here you can see that the sigma 1 is negative. It means that the sigma 1 will be of a compressive nature, and sigma 2 is positive, so it will be in the it will be of a tensile nature. Okay, so the figure will be like this. So you can see that sigma 1 is it acts in a compressive manner and sigma 2 acts in the tensile manner. Similarly in the third quadrant here you can see that sigma 1 and sigma 2 both are negative, means sigma 1 will be compressive and sigma 2 also will be in compressive state of stress. So the figure will be like this. Okay, so here if you'll see both stresses are having same nature. Okay, also in the first quadrant you can see that both stresses are having same nature. In the fourth quadrant sigma 1 will be positive, it means that it will be tensile nature, and sigma 2 will be negative, it means that it will be of a compressive nature. So here you can see that the stresses which are acting in y direction are of a compressive nature, and stresses which are acting along the x-axis are of a tensile nature. So these in the second and fourth quadrant you can see that the nature of principal stresses which are acting on the component are having different nature, that is mixed nature, but in the first and second third quadrant you can see that they are having same nature. Here you can observe the tensile state of stress for the both maximum principal stress and minimum principal stress. Here you can see that the compressive state of stress or compressive nature for the maximum and minimum principal stress. It means that for plotting the safety region we need to consider the here you can see that I have given the limit sigma 1 should be less than SYT, sigma 2 should be less than or equals to SYT. Similarly sigma 1 should be less than or equals to SYC, that is the yield strength in compressive, and sigma 2 should be less than or equals to SYC, that is yield strength in compression. So let us plot the region of safety. So here once again I am going to take two axes. On the horizontal axis I am going to plot the sigma 1 on towards the right side of origin. I am going to consider the positive stress. Positive sigma 1 means it will be in a tensile manner. To the left side I am going to consider this as a negative stress. It means that it will be having the tensile compressive nature. Similarly on the y-axis I am going to consider positive sigma 2 and negative sigma 2. Positive sign is representing the tensile nature and negative sign is representing the compressive nature of the stress. Okay, so similarly on the origin on the x-axis, here the first is sigma 1 should be less than or equals to SYT. Okay, so here I'm going to assume any value of SYT. You can take 200, 400, 300 Newton per mm square. Obviously it will be the value will be, or the magnitude will be same for the tension and for the compression also. It means that SYT should be equals to SYC, that is yield strength in compression. So I'm going to plot for the value of sigma 1 is equals to SYT. It is the maximum limit beyond which the stress should not go, otherwise the component is going to fail. Once again I'm going to repeat that the value of sigma 1 or sigma 2 should not be greater than SYT or SYC. Okay, otherwise the component is going to fail. And here we are going to plot the region of safety. So first is here you can see that sigma 1 is it should be less than or equals to SYT. Okay, so for the value of SYT I'm going to plot this is the positive value. I'm going to plot this towards the right side of the origin. So somewhere at here there will be a point. So this is actually this length of the x-axis from the origin. It is actually representing the magnitude of SYT or the magnitude of sigma 1. Similarly on the if you consider the sigma 2, that is the minimum principal stress, it should be again less than or equals to SYT, that is yield strength in tension. So on the y-axis there will be one more point. Okay, so this from the point origin up to this point, this is the region of safety. If the sigma t is going to exceed above this, or if the sigma 1 is going to exceed above this, the component is going to fail. Okay, similarly for the value of sigma 1 less than or equals to minus SYC, so a minus sign represents the compressive stress. So this is the yield strength in compression. So obviously negative on the negative side or on the left side of the origin I'm going to plot the SYC. Again I have assumed that SYT and SYC both are having same magnitude. Okay, so here on the same distance or on the same magnitude there will be a SYC. Okay, this is the negative side. Similarly for sigma 2, that is the minimum principal stress, which should be less than or equals to yield strength in compression. So at somewhere at here this is the minus SYC. Okay, so remember one thing, that while designing brittle material we are going to apply the maximum principal stress theory, because the brittle materials are weak in yielding and we are designing the component on the basis of yield strength, okay, in tension and compression. Okay, so particularly this theory is only suitable for the brittle materials. This is not suitable for the ductile materials like the shafts. While designing the shafts we usually we do not use the maximum principal stress theory. Okay, so I'm going to draw the lines, vertical lines, okay, and horizontal lines from these points. So first is in the first quadrant I'm going to draw a vertical line, okay, from the point SYT, that is sigma 1. Similarly from the sigma 2, that is SYT, I'm going to draw a second line, horizontal line. So at the intersection point I will call it as A. Okay, similarly for the second quadrant for the value of sigma 2, positive SYT, and negative SYC for the value of minus sigma 1. Okay, so I will call this at the intersection point, I will call this as B. Similarly for the negative sigma 1 and negative sigma 2 for the compressive stress, that is yield strength in compression SYC, I am going to draw a vertical line and similar a horizontal line from this point. Okay, so at the intersection point this is the I will call this as C. Similarly for the fourth quadrant this is D, and this region ABCD, if while designing the component if you will get the value of sigma 1 or sigma 2 within this region or inside this region, then the design will be safe. Okay, so this is the actually the region of safety. Remember that this value of sigma 1 should not exceed or it should not be greater than yield strength in tension or yield strength in compression. So or you can consider this as it should not be go out of this area. Okay, inside this area your design will be safe. Okay, thank you.